is actually two papers, both by these guys named Sylvain Lefebvre. He's got it's V-V-R-E, so however the hell you pronounce that, and Hoppe. And one paper followed the other, so they came up with this first paper called Parallel Controllable Texture Synthesis. And this is the paper that I had to read in order to fully understand how this one worked. And before we start with any of these things, let's talk about what we mean. So if you've ever played with texture synthesis, what you typically do is you have an image we're going to call exemplar. And it's got something in here. And now, my little Chalk Talk announcement, I said, puppies. This stuff doesn't work with puppies. It never will work with puppies. It works with regularly repeating patterns. They don't have to be tileable, but what you want is something that kind of looks the same no matter which way you look at it. That's one of the key things. It doesn't have to be exactly the same. It can be grass, it can be blah, or whatever. But the main thing is it has to be something where you can conceivably do one after the other after another. You can zoom in on this section and you go, oh yeah, that kind of looks like the thing I started out with. Or I can expand it out. Oh yeah, it kind of looks, it has sort of this self-similarity stuff to it. So if you have, totally forget what are they? If you have a picture of a puppy or a big tree, puppies aren't self-similar. You zoom in on a puppy and it looks non-puppy-like. If you zoom way out, then what you're seeing is mostly the background of whatever the puppy was sitting next to. And so again, it kind of looks non-puppy-like. That's not the way these things work. It has to have some sort of self-similarity if you even give it a chance. And believe me, I know this from personal experience because I've written a couple of texture synthesis algorithms thinking, oh, this is cool. The first thing I do is hand it a puppy and it doesn't work. You have to make sure that you give it stuff that it can handle. Now, the basic idea from way the hell back is saying, look, I wanna recreate this, but way, way bigger. I wanna make something huge image that looks kind of like this, but not exactly this. I just don't want to stamp this one after the other onto here. Because this thing isn't tileable. If you did that, you'd see that I stamped that 4 times. But what I'd rather like is something that kind of has, it's probably got higher frequency. I mean, these wiggles are going to happen more often, but it's going to look sort of like the original thing, but much, much bigger. So the way that happens is that you start thinking this in terms of pixels. And the first one to actually produce something that sort of worked was a very simple concept. Where they said, all right, we're going to start off, we're going to pick a pixel. We'll pick a pixel randomly from this point. We'll go that pixel there from the exemplar is going to get plopped into this. And then what we're going to do is to try to decide on this next pixel what should be its color. Where we want to use this as a guide. Now naturally you'd say, well, if this guy is here and that guy was there and we just moved over to the right, well, I'll just use the one to the right. That's going to give you copies. It's going to give you stamps and copies when you're not doing anything exciting there. Rather, think about this. Let's assume farther on that we somehow magically have actually created pixels up to, let's do this. So this whole row has gotten created. This whole row and this whole row has gotten created. And we've created this, and again, magically kind of happened. And it looks good. We're happy with it. These pixels there that I've sort of outlined are good. They come from there. They look like this, but they don't exactly look like this, but they're still looking good. And instead of that pixel, which is kind of a little weird, what about this guy? And we're going across. We're doing all these pixels over here. We're doing all these pixels. I'm not going to draw them. And then we came to this guy and we go, what about that guy? Well, here's the basic idea, is that they said, okay, well, we kind of know some information around this. We know what this pixel and this pixel and this pixel. We have 4 pixels here where we kind of know that, hey, we've got a good pattern going on. So here's the idea. Why not go around in a 3x3 neighborhood and sort of take these 4 pixels, these guys right here, and compare them to this image. And so I'm gonna go through here, and remember, these pixels are not exactly stamps from this image. We've somehow created this before. And so I'm gonna go through there, and I'm gonna slide this 3x3 little window across all the pixels in this exemplar thing. And maybe this exemplar is 40 by 40 pixels here. So you just sort of slide it through here, and for every pixel as you slide it through, you're going to give the position a score. So in this case, I have this line going through here, and again, this is a pixel, so this line represents a color. If that color is correct, and here the line is actually going through the middle of the way I've drawn this, and so let's assume that that means that that color doesn't match. So the score on this one might be a little low. You're going to say those 4 pixels right there don't really correspond to those 4 pixels there. Yeah, I'm not happy. But maybe over here, I'm going to try to draw it this same way. I have my window, and I haven't drawn this aligned, but all these, the search I'm doing is very much pixel aligned here. This window might have a much higher score. So that might be a high score of match, and this might be a low score of match. And as I do this throughout this entire image, I'm going to produce a big list of how well each one of these little windows matches what I've got. And so each one of these pixels is going to have a score. And we can sort them. We could say, this guy, and that guy, just picking at random, have the highest scores. And then we can even do some more stuff, because we don't want to make sure that every time we see that, we get the exact same thing. We want this to look the same, but be different. And we want it to have a little variation as it goes along. So what we'll say is, we can say, all right, let's find, so step 1, use search area, or search, use what we know, search to rank pixels. Then, based on the randomness, and this is a user settable thing, user settable randomness, choose, I don't know, n of the best fit. And so in here, I choose 3 of those guys. And then of that, pick 1. All right. Now, what does that mean? Well, that means I'm going to take the color from one of these things. I'm going to just randomly choose between the n best fits that I found. And I'm going to choose that color. And I'm going to plop it over there. And I'm done. I'm done. I'm actually done. I mean, I just took that color and blorped it over there. And so that means that that point now has a color, and we can now go back and do the exact same process for this guy. So, as we're moving along, you can see that we're going to be choosing colors that are in the center of this thing that have matches to the area around it. And because of the randomness, we're not going to get exactly the same pattern that we originally started with. We're going to get things that are plopped around. And when you do this, it actually works. It's kind of cool. All right? Does that make sense? Yeah. This is how this works. This is the very first thing. Now, when you first do this, if you try this with a 3x3 pattern, you're going to get a lot of crap. It's going to look kind of the same because, and notice one other thing, I don't actually ever create a color. When I take colors to create this thing, I'm actually copying them from here to there. I never interpolate, I never do anything. I'm just copying colors. That's key, because you're never going to get anything too far away from this. It's always going to be about the same colors. Whether or not the patterns work the same is going to be weird. There's a couple of problems with this. First of all, it's super, duper slow. because you're walking through pixel after pixel. Let's just wheel it. And you're doing this huge search, and then you're going around and doing pixel after pixel. And so this all started, I don't know, 1997 or something. I think it was one of the first texture synthesis paper, I think, somewhere around there. And it was like, hey, this is kind of cool. This kind of works. But super slow. This search is brutal. And if you use 3 by 3 pixels, you're going to get crap. It looks like going to look like appropriately colored kind of oatmeal that has some sort of suggestions where you look at it and you go, that's kind of cool. So the first thing you do is you don't use 3 by 3. You actually use 5 by 5. And then all of a sudden that makes your scoring a lot better so that you're only going to find matches. You can easily sort of see that, hey, I'm going to find a match here where maybe it's not. Just because of the way the pixels work, it says it's high, but it's not. It doesn't say, you know, something that was minus and then plus, and you add them all together, and it gives you sort of a false positive. Well, bigger areas are going to make that much harder to do. The problem is, of course, bigger areas are going to be slower to compute. And then if you make them too big, then you never get the randomness that you're kind of looking for. So there's all this sort of balancing with texture synthesis about how to coerce this kind of scheme to produce good results. All right, so that's what we're doing. It actually does work. If you look at some of the, I can bring up the, essentially, might as well. I'm going to quickly pop over here, and I'll tell you where I'm going in just a moment, but I'm going to pop over, or I can share the screen with you guys. I'm going to, if you do Google search on texture synthesis or appearance, there's a lot of good examples, and there's one guy who was, oh, this guy, I think, yeah. Yeah, here's a good thing. So hold on, let me go. For people watching on YouTube, I'm at this guy's name, Alex Rubinstein's texture synthesis example paper. Let me make this big. You can kind of see, what the hell happened? Where'd it go? Come back. There we go. Just a moment, I'll share screen. Okay. And zoom in, and you can kind of see, like, and by the way, this is a better algorithm, but you can kind of see here's a source, the exemplar image, which is nicely self-similar. We're happy about that. 3 by 3 window, oh, you know, boink. 5 by 5 window, you're starting to see some cool stuff. You know, you're starting to see some of this stuff. Bigger windows get better and better, but of course, this is getting slower and slower. This one actually looks a little bit too regular, and so you can almost sort of start seeing that, hey, I'm basically reproducing the texture over and over again. So you really want some of this controllability about how much this all matches. But it does actually work. Look, 3 by 3 window, suck-a-doo. But as you go up, you're starting to get some interesting stuff, and so on. Oh, and this one, yeah, this one's a whole different algorithm. The Efros and Leung algorithm is one of the first ones that really started to work. This is a total different thing. You can get some really bizarre behaviors, like this guy with this thing. Or, you know, yeah, this is where you try texture synthesis thinking that will solve all your problems, and then you realize it doesn't. It's just like, this is crap. All right, so there's some background for you. Let's get back to the original. Here I am. So now, flash forward and switch over the camera. We're going to go to this paper called, and before we get to the appearance thing, then this talk is not going to have much math because we're just not going to have enough time to get into the math, but we will get into a little bit. So these guys came up with a paper that's very cool, called Parallel Controllable Synthesis, and it's by the same authors as the paper that we eventually want to get to. And the first thing they did is they said, hey, you know, these kind of techniques are fucking slow. So is there some way that we could possibly make them better? And so I'm going to zoom in here and talk a little bit about exactly what they do. So they do. They have a way of doing this that uses an image pyramid. So first of all, there's a couple of things we're going to talk about. They have, once again, an exemplar. But, I'll put in our little wavy lines again. Wavy lines, leopard spots, or whatever we want to do. But they also say, look, we all acknowledge that what we're going to do is copy points from here to there. But in order to make this a little bit easier and easier to manage, we're going to have a UV map that goes along with this. So this is a UV map that goes from 0 to 1 and 0 to 1. And they plot it out, and it's just a gradient that goes across here. So this is just a value where if you look up a value in here, you're going to get a UV coordinate that corresponds to that. And so if this goes to 0 and 1, initially this is just all zeros and ones. But what they're eventually going to create is a UV map that's associated with the image that they want to create, which is like saying, hey, I want to suck this stuff from there. And it's just one extra step that they allow you to do some stuff. So this is an M by M, so square image exemplar. And what we want to do is create synthesize an image S in which each pixel S of P stores the coordinates U of the exemplar pixel that we want. So we're going to create, we've got our target thing here, S. We're going to synthesize this image, S, where each pixel stores the UV coordinate of where that pixel comes from in that image. Okay? All right. So the color at any pixel P is given, and right. So E of, here's some math, look out, E of U, which is the UV coordinate, is equal to E of S of P. Now what does that mean? Well, S is our target thing. And so this is just a mathy way of saying, if I've got a point at a pixel at pixel location P, so this is all just part of pixels, here to there to everywhere. So that's a pixel up and a pixel down and all that kind of stuff. And if we say that that is pixel coordinate P, and what we do is we look up the color, right? This is a color at that pixel. The red channel is the U value. The green channel is the V value. And we use that U and V thing to jump over here and figure out what the actual color of our pixel is. So this, the color of this S image at a pixel turns into a UV coordinate that we use to map over to there. It seems like a little confusing, but they really do a lot of the sort of math on this, so that they are working mostly with UV coordinates, and this is just sort of an after effect. You know, they have to go to the exemplar, but this is how they're dealing with it. So at the end of it all, they're going to produce, this is kind of cool, they're going to produce a couple of things. They're going to produce an image pyramid of S's. So there's going to be S0, which is one size, S1, which is twice the size, S2, and each one of these is going to contain UV coordinates, right? And each pixel will contain a UV coordinate that goes back to the exemplar. And from this, because I know how to create actual pixel values, I can create my exemplar based on S0 just by taking all the pixels here, looking them up in this exemplar and plopping in there. And then an exemplar based on S1, and then an exemplar based on S2. Right? So this is important. So given an exemplar, we synthesize its coordinates into a coarse-to-fine pyramid. So this row shows the corresponding exemplar colors, and if I could actually draw this, these would look wavy lines. So all these guys would have wavy lines. These guys, if you look at them, look for crap because they're UV coordinates where the red channel is U and the green channel is V. And you look at it and you go, what the hell am I looking at? Well, it's UV coordinates, so it's weird. The cool thing about this, if you do look at them, is that there are all sorts of these blocky areas. They have overlapping sort of colors of blockiness in here, which makes sense because the way these texture synthesis works is once it starts copying values from an area, it continues to copy values from that area for a while. And you'll start getting repetitions of this, but only for a while. And then I'll switch over to another area, and then I'll switch over to another area. So these little blocks in this UV coordinate image represent little areas where we've chosen from the same blob in the exemplar image. And then that gets bigger up here and so on. So these all look like wavy lines. And the same number of wavy lines, right? Because, right? Yes. Because each time this is just an image pyramid of the same thing. So this is just half the size of that, is half the size of that. Now, why are we doing this? Why are we doing this? Remember, with our original example, we were doing pixel by pixel by pixel in the image that we wanted to generate. With this, what they're saying is, hold on, don't do that. Don't do it that way, because that's slow as all get out. What we're going to do is start out trying to create a low-resolution version of our image. So instead of doing this very detailed image right from the get-go, we'll do a little teeny version of it that looks like a little teeny version of our exemplar, fast. We'll do it really quickly because it's really small.
Well, and you can use a 3x3
kernel. Exactly what he said. The 3x3 kernel works really good in here because that spans a large area, right? It can get away with it. So then we go up to this one and we use what we got here to inform this. So now the search isn't nearly as crazy. We don't have to search the entire image. We can say, hey, we're happy at this low resolution thing that we got fast. In fact, so fast that they built this algorithm so it works with the GPU. So they're doing what the previous algorithm took minutes to do. They're doing almost real time for the same size image and better quality.
So you're building the S images as you go.
As you go, both of these are getting created. So the S images are the UV mappings, right? The E the E is just sort of an afterthought. You don't even have to create this. Well, you kind of do because you're going to do some comparison. But it's kind of like you don't even need to actually create this because you can create an E sort of automatically by just going to the S and saying, hey, look up those UV coordinates. If I want to know the value of this pixel in or this pixel in E, I just choose the UV coordinate of this same pixel in S and look up that
you
value.
need E sub 0 to make S sub 0.
S sub 0 makes E sub 0. That's sub S sub 0, right?
No, I thought that ES sub 0, ES sub 1, and ES sub 2 were just taking the exemplars and making a map.
Unfortunately, they use some weird notation here. But this thing, we synthesize, so given this, we synthesize its coordinates into a coarse-to-fine pyramid. The bottom row, which is this, shows the corresponding exemplar colors, not necessarily the exemplar image, right? So this is the image we want. This is the 1,000 by 1,000 image that I eventually want to end up with. There's only one exemplar. This.
It's like instancing.
Exactly, yeah. It's like instant. Well, perfect idea.
But those are that's the product, the E sub SO.
Yeah.
So the biggest one of those is the output.
Yep. This is the one we want. We want this. But in order to get this, we have to create this, which gives us, from that we can get this. And then, once we have this, we can use this to inform how we create this one. So this one is going to be a creation starting from here, but based on that, and then blah, 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 blah. We're going to walk our way up.
Question, Dick?
Yeah.
Is the fact that you're only working with U and V, so 2 values instead of the 3 for RGB, do you get any time savings on that, or does it really not matter?
No, but excellent question, because I'll explain in just one moment, because that's a good one. All right, so, okay. So now, so let me see how to explain this. All right. The best way, I'll show you the best way, is to write down an algorithm. So not too much math yet. I probably shouldn't erase that, but I'm going to do it anyway. So let me keep this around. Exemplar. This is the input image. That is M by M and has wavy lines. That's the thing we want to repeat. Here's the algorithm. So synthesize, and this is it. Parentheses. So we start off with S -1 equal to zeros. Right. So what does that mean? S -1, we call this one S0. And S0 is going to be, at a very basic, a 2x2 image, because this is an image pyramid, right? So for this to all work, we need an S -1 so that we can actually start this thing off. And we're going to say that S -1 has the UV coordinates of U, or 0 and 0. All it is it gives you the bottom corner of this picture. All right? Then, for resolution level, so we're going to traverse up the tree, and we'll call this L, which is an element of 0 to L. So we're going to start it out at 0, which corresponds to S0. We're going to go to 1, twice the size. That'll be a 4x4 image. Go to 2, that'll be 8x8, until we get to L, which might be 1024 by 1024, or million whatever by million whatever. We can make this go as big as we want, as long as it's power 2. All right, then we're going to do 3 steps. S1 is equal to upsample S L minus, SL, sorry. Look like a 1, but it's just small. All right, so we're going to upsample the whatever thing we've got. So in the very first thing, we're going to take 0, 0, 1 pixel that is 0, 0, and upsample it to a 2x2 thing, which is going to be a whole bunch of zeros. Then SL is going to be equal to jitter. This is clever. SL. So we're going to perturb the coordinates. Now, this is kind of cool in that we're going to remember, and this is why we want this UV thing, is we're going to wiggle these coordinates a little bit. Right now they're all zeros, especially in the first level. And to start everything out at 0, 0 is going to be a little boring. So what we're going to do is wiggle them a bit. We're going to make them move a little bit. But the neat thing about this is as we do this on each level, the wiggling that we're going to do is going to be constrained by the level. So at the first level, wiggling a 2x2 pixel is pretty much going to let us move wherever we want on this thing. We're going to add 1 or subtract 1 from the pixel, and we're just going to move around here. But as we get farther, adding 1 or subtracting 1 from the UV coordinate is only going to move us within that little chunk. So when we get to the 4x4 area, then changing the perturbation of this will only move us a little bit in that little area, corresponding to sort of the resolution of our S. And so as we get farther and farther up the pyramid, the UV coordinate stored in S is only going to stay within it, the local area that it's at. At the very beginning, the local area is the entire image, so it can move all over the place. As you get farther and farther up, what you're going to be doing is just refining what you've already found, which is a really clever idea. All right? So, all right, upsampling, by the way, relatively simple. They're just going to make the image bigger. You do have to, when you upsample this, it isn't just copying the pixels. They want to also incorporate the fact that if I take the UV coordinates that I found in here and move it up into this, I'm also going to have a sort of spatial slide in there. So think about this. If I've got a UV coordinate here, whoop, it points to this pixel. And then I upsample it. Well, when I do that, if I just took the UV coordinate that I had here and copied it, bloop, 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 that means that each one of those guys would be getting it from the same pixel, right? You get the same color. That's not exciting. But this is all area-based. So as I upsample this, I'm going to copy this over, but then realize, hey, that pixel is actually a little bit over. There's a delta involved in there. And you'll see this actually in this paper a lot. There's this, that's not delta, that's another Greek thing. That delta is this, but whatever the hell that is, capital theta or something. This comes into play, and they add it to the UV coordinate.
Delta is the upward pointing one, and del.
Right, that's right. Thank you very much.
Yeah.
Your voice sounds so angry.
You were right.
Yeah.
It's delta.
That's delta. Yeah, that is a delta. Okay. And delta is really easy. It's the deltas are just 1, 0 in that coordinate space. So this will just basically move those guys so that instead of having UV coordinates all at the same place, they've got UV coordinates in the local neighborhood of that. Notice, it isn't, I didn't put this guy here, right? I didn't put it up in the upper corner there because that's not the UV coordinate. UV coordinate is wherever it happened to find a good match at this point. All right? So that, the upsampling, makes that lower level image bigger, but then also adjusts the UV coordinates in there so that it stays within the same area. And the jitter is interesting, where they say, hey, you've got another randomness kind of thing here that we can do, where we're going to move these guys around. But again, it's going to be in the same scale space of this. So each one of these guys will get jittered kind of randomly in this area. And as we get higher and higher up, that arrow size, if I've got this point, might be just a little jitter and only move just a little teeny bit. But when we're down in 2 and 4 and 8, it's actually a fairly large thing. All right? We won't even do the math for that, but it's relatively simple. Then, what you do, and there's an if statement here. So if L is greater than 2, I say for all but the 3 coarsest levels, we're going to apply a correction pass. So the first 3 levels, and the 0, 1, and 2, are just upsample and jitter. You think I read that and I was like, what? Why are they doing it? And the reason they're doing that is just to kickstart this thing off with just a completely random UV field, right? So they upsample 0, 0, 0. That'll give you 4 coordinates. They wiggle those coordinates, and then they upsample that again, wiggle them some more, and wiggle them some more. And by the time you're done with 3 levels of this, 0, 1, and 2, your UV S image is just a whole bunch of random numbers. It's just random. So now, what we do is for 1.c, we're going to do correction passes. And so the number C is the number of passes we're going to do. S sub L equals correct. S sub L. All right. So the correction pass takes the jitter coordinates and alters them to recreate neighborhoods similar to those in the example. All right. So for each pixel, we gather the pixel colors of its 5 by 5 neighborhood. Remember, we talked about that 5 by 5 neighborhood. And this is why we don't do it at the very lowest levels, is because that 5 by 5 neighborhood, which they stick with the entire time, they only use 5 by 5. 3 by 3, I think, is a little small. Is good at that level. And each time you go up, that's all you need. So what they do is they take those pixels, put them in a big vector, and then they compare in the neighborhood of this area. They don't do an entire image search now. They only look in the neighborhood of where these pixels match to, and do that thing again, where you find the best match. But notice what they're doing here. This is kind of cool. The previous one, as you went along, you're only using sort of the top part of the image in order to figure out the texture thing. That's an old way of doing this. This time, they can actually compare all the pixels in this image with the exemplar location. So they can go through here and sort of say, okay, all the pixels, because I have an example, even though it's a low res kind of thing, how does that fit inside this thing? So that's pretty actually relatively easy to do. And they do some stuff. The other thing that they do is they take all this stuff and apply it so that it runs really quickly. So this GPU-wise, check. This one, super easy to do GPU-wise. That's another check. This is just a little plus and minus 0 and 1 on the GPU, super fast. And then it turns out that this, the way they formulate it, and we're not going to go into that because we're going to get to the next paper, is also GPU-able. So what this means is they can do the upsample in one GPU pass to all the pixels in the image. They can jitter all the pixels in the image in one GPU pass. And then they can correct it. Each correction is going to be, it doesn't even matter what the other pixels are. You can do one correction in one GPU pass, like that. And you do that C times to make sure that the correction actually works correctly. The reason you have to do this is because each pixel is being done independently. So remember, it's all a neighborhood kind of thing. So if I have and correct that pixel C, and then I also do this one D slightly at the same time, the fact that C changed colors would actually impact what D should be. So what we're going to do is just do the whole image, the whole image, and the whole image. And each time when a pixel color changes, it's going to affect its neighbors. Now, if you did this enough, and the hope is that if you did this enough, eventually you'd stop changing colors, because all the little corrections, the matchings, would give you, neighborhood pixels that would look good, that you'd be happy with. This is one other thing about this. There is no randomness here. No randomness. Remember how I said find the best matches of the 3 best pixels that fit in the original algorithm? That's gone. This is just saying, given the location of the UV coordinate for a pixel in this in that image, give me the best match in the local neighborhood. So the randomness happens here. We're going to be wiggling those UV coordinates, but this aspect of it is completely unrandom. We're just correcting until it eventually solidifies. And because this all happens in the GPU, like I said, it can be done in milliseconds instead of 15 seconds or however long a texture synthesis happens. All right. So now we're happy. Everybody can write this. The cool thing is now we can go to this paper. In this paper, they had an idea. They had a brainwave. They said, And quite frankly, there were other people who had laid the foundation of this. But here was the thing. When I correct this pixel, what am I doing? I'm looking at the neighborhood of this pixel. And let's use a 3x3. I'm going to take this color and this color and this color. No, this is UV coordinates, so I'd have to go here. This color and let's draw it correctly so everybody knows what I'm talking about. So if I want to correct pixel C here, what do? I know the colors of each one of these pixels, right? This is an actual image. This is UV coordinates. So if I want to correct this pixel, what do? I go and take the color here, and all these colors, and I'm going to put it into a great big vector. I'm going to make a vector where each one of this is red 0, green 0, RGB, and that's 0. We'll call that 0, and this would be R1, G1, E1. And that would be 1, 2, 3, and dot, 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 all the way down. And then what I do is I come back over here, and I look at areas just like I used to do, where I'd say, okay, here's my little exemplar area. I'll make a vector that looks like that, and I'll compare the two. I'll do a dot product and take its square root and figure out how far away those vectors are from one another. How close do those pixels look like they actually belong? And then I'd search around here. I'd do a little neighborhood search to find the best example, the closest color, or this great big long vector of colors that matches that area. So, pretty straightforward. You're just matching little areas of red, green, and blue. And said, hold on. There's a way to think about this where we can actually put some more information in there. I mean, just making this look like the red, green, and blue matches the red, green, and blue of those things isn't exactly right. What we want is, we want features. We want the appearance of this, not just the color. And the appearance means things like, well, the shape of whatever you're looking at there, or whether this has an edge, or whether even how light reflects off it. So this is the thing that they did here, is they said, okay, let me get to the page where they actually did it.
In the first paper, the correction algorithm uses the color
Yep.
because it's operating on the UV map.
UV map, again, is just a way to get from the color of the image that you're building at this time to where it came from in the exemplars. So here, if I wanted to know the color of that pixel, I go and look up the corresponding UV coordinate in the UV map.
And that directs you.
And then that comes and tells me that that color is coming from this pixel. Now, this color might not be coming from the pixel right above it, right? That color might be coming from someplace else. And that means that this UV coordinate might not necessarily be the UV coordinate directly above this pixel. But that's okay. If I want to know the color of that pixel, I go through here, and then I find out where I am here. Same for this. If I want to know the color of number 2 here, I go up to here, and then I jump over there. But I still have to come back here to figure out what the original image looks like. So what I'll do is I'll use my mapping to create this vector. And then I use the fact that this guy is at this location in here. Now I'm just looking at C. And that tells me the area that I need to look at, right? So area here, now I search around this area where I'm actually comparing this vector to similarly created vectors from this image. There's no UV coordinates in this image. I'm just looking at nearby neighbors. But then, when you're reading this, oh my God, is it complicated? It's like, what? You asked me, you what? Why? But at its basic thing, this is just a little way of jumping from one thing to another. All right, now, here's the thing. I said, wait a sec, let's look at this vector thing that I've created. All right, Distance typically is measured by summing the squared color difference, right? We're going to look at the comparison of this. Because each pixel only contributes information at one point, large neighborhoods are often necessary to accurately recreate the original texture structure. So what that means is, remember what we're doing. We're comparing this color at this point, but we can't just do one color. We have to actually look at the 5 by 5 neighborhood, or in other algorithms, bigger neighborhoods all together. So what does that mean? Such large neighborhoods are a runtime bottleneck. So even though we're doing this at various levels, having to look at that whole neighborhood is a pain in the butt. So what they said is, okay, what we're going to do is we're going to recognize that the set of image neighbors typically lies near a lower dimensional subspace. We'll explain that in just a moment. Our insight is to apply neighborhood projection on the exemplar itself is a pre-computation. And so what we're going to do is say, wait a sec, maybe we can encode this neighborhood that we're looking at in this exemplar in a clever way. And make sure I get the right thing here. All right, okay. So what we're going to do is create a new exemplar called E prime. So this is now this actual paper. So we're going to take this thing and we're going to try to take these neighborhood searches, these areas that we're looking at. Maybe it's 5 by 5 or 10 by 10 or whatever. And we're going to try to encode that in a new image. All right. This is the cool part. We're going to if I've got, well, and let's stick with 5 to 3 by 3 just because it's easy, but they never work with 3 by 3 just in case. If I've got a 3 by 3 pixel over there, or an area that I want to compare with this guy, then what I have to do is create a big long list of things there, and then compare it with a big long list of things here. But they said, wait a second, hold on. If we do this, if we pre-compute these big long lists of things, so for this pixel right here, I'm going to create a big vector, RGB, and this is 0, 0, 0, 1, 1, 1, all the way down to, well, this is 9. So R8, G8, B8, right? And then I do it for the next one over here. So that goes to that pixel, but now let's do this pixel right here, the neighbor to that. So this guy's going to create that. R0, RG0, and notice it's been shifted over, so this is not going to be the same thing, but it's going to be the same thing all the way down to B8. And if I do that for the next one, and do that for the next one, all of a sudden I'm building a matrix, right? I'm building this big long list of pixels. Then I can do a dimensionality reduction. And what that means is we're going to use principal component analysis. Principal component analysis is this really cool stuff that we've talked about lots and lots of other chalk talk. And quite frankly, I think it's about time we do another principal component analysis chalk talk, but we're not going to be able to do that here. Which basically says that we're going to take this stuff and compress it. We're going to say, you know, each one of these things is like this multi-dimensional vector that represents a spot in this n-dimensional space. But you know what? Most of that stuff is pretty much garbage. That n-dimensional space is way too much information. What we're going to do is look at that n-dimensional space and find the 3 biggest components, or the 6 biggest components, or something. So principal component analysis, by the way, let's just quickly, in 1 minute, do a thing. Say I've got a cloud of data points that I have sampled. Like this is temperature is this way, and frizziness of hair is this way. So low temperatures mean low frizziness, high temperatures mean your hair gets frizzier, right? And we've done a lot of sampling where we've asked various people, and they all agree that, hey, when it's 10 degrees, my frizziness is 20%. And when it's 80 degrees, I got 100% frizziness. And I get a sample thing for that. What we want to do is sort of say, okay, that cloud is kind of hard to look at. What would be nice is if I could figure out the principal components of that cloud. Actually, and since it's a two-dimensional thing, there would be two principal components. The sort of major axis of the cloud and the minor axis of the cloud. And one of the cool things you can do is you can say, all right, for this minor axis, I'm going to throw that away. I'm going to say that this thing is so small compared to the major axis. That major axis, when I do this analysis, is so small that it really doesn't matter. And I can project all these points down onto this major axis. So that point goes there, this point goes there, this point goes there, blah, 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 blah. And we're basically saying, you know, this stuff doesn't, this extra stuff here doesn't matter. It's this line that I care about. And all of a sudden, I have a clear mapping between temperature and frizziness that pretty much holds for the entire world. And now I can create something that says at 80 degrees, your hair is going to be this frizziness. And I can actually say that there's a plus and minus error on this, but this is a line that represents that. Well, this is the same concept. Instead of 2 dimensions, which is easy to visualize, this is actually, well, for this, it would be 18 dimensions. Blam, your head goes, 18 dimensions, I can't handle that. But quite frankly, yes, you can. It's just 18 dimensions of this, and there is this line out there that is the most important dimension. It's a weird dimension. It doesn't look like anything, but it's there. So if you plotted this out, you'd get this weird cloud in 18 dimensions, but it would still be a cloud. So what we're going to do is use PCA to take this down, instead of 18 dimensions, 3 dimensions. And the way you do this is you get those vectors out of PCA. And by the way, this is trivial. It isn't trivial by any sort of means, but because people have been doing PCA for so long that there are just algorithms that can do this. So you just ask it whatever you want to do. So that 3 dimensions, well, wait a sec. That means for every point on this image where I created one of these vectors, I now have a 3-dimensional number that represents what the most important parts of this image is. So now this E prime is going to be a similar image to E, but now instead of having RGB colors, I have these funky ass alpha, beta, gamma colors at each one of these. And if I store these principal components, when I create this thing, I can project this down the same way, right? And so now if I want to figure out whether this color or this area here matches, I don't have to do a 15 or 18 color match. I just have to do a 3 color match. We're gonna get kicked out. Somebody else wants to come in here, so answer. And the best part about this is that once you start thinking about this, instead of just colors, you can also.
I think we have joined a meeting still in progress.
We're almost done. We're almost done. We're just doing a little bit more now.
Okay.
So instead of just colors that you can do here, you can also do things like edge quality. So you could have edge 0, edge 1, edge 2. You could do edge detection on this. Or you could even have, what they have is a user-definable mat, where you could say, hey, this area right here is really important, and I want that to be part of this. So you can have all sorts of controls about how the texture transfers over there. The whole framework stays exactly the same. This is all just about how you compare one color to another. So cool. Such a clever idea. And it gives them so much power. We may do another section on this because the other things that you can do with this is, since you're doing a UV coordinate kind of thing, you can actually warp the UV coordinates so that you can say, when I'm generating this texture, I want it to flow in this direction. And you can even have, they even use this technique to put foam on water, where they have a foam exemplar, and they say, I've got an ocean, put foam on it, but also make sure that the foam moves as the ocean does. So clever, and that's just by warping the UV coordinates of this thing. Make sense? Sort of? Sort of? Everybody write it up. It's easy to do in Python. Bye, y'all.
Do you have any Python examples?
Well, actually, I'm not kidding. What?
Do you have any Python examples?
I'm actually writing this up in Mathematica, so I could do that. I can turn it into Python.
Mathematica license.
And we have a MATLAB license too.